Somewhere above your head right now in low Earth orbit, a handful of satellites are quietly running some of the very first data centers ever built outside our planet. Not science fiction, not a distant concept sitting in a PowerPoint slide somewhere. Real hardware, already launched, already processing data hundreds of kilometers above the ground. And now, a small but growing group of companies and space agencies are asking an even bigger question. If classical computers can run in orbit, why not quantum computers too? The answer they're arriving at is starting to look like yes, and the implications are stranger and more urgent than most people following this story realize. Let's start with what's actually already happened, because this isn't purely speculative anymore. In January 2026, a company called Axiom Space launched the first 2 dedicated orbital data center nodes into low Earth orbit. These systems operate using an optical relay network built by a company called Kepler Communications, giving them Earth-independent processing capability, meaning they can crunch data directly in space without needing to constantly beam everything back down to the ground first. This followed an earlier prototype Axiom had already tested aboard the International Space Station, running cloud computing and artificial intelligence workloads directly in orbit using edge processing infrastructure. Why would anyone bother putting a data center in space in the first place? The core argument comes down to a few very specific advantages that Earth-based facilities simply cannot match. Satellites in orbit have access to constant, essentially unlimited solar energy, without cloud cover, weather interruptions, or the day-night cycle, limiting how much power reaches solar panels. Space is also naturally, permanently cold, offering passive cooling that costs nothing compared to the enormous water and electricity resources Earth-based data centers burn through just to keep their servers from overheating. And, crucially, for satellites that are already collecting enormous amounts of raw data, whether that's imagery, telemetry, or sensor readings, processing that data directly in orbit means you don't have to send every single raw byte back down to Earth. You can filter, compress, and analyze it right where it's collected, sending back only the results that actually matter. This is exactly why the space data center race has exploded so quickly over the past year. A 5-month-old startup simply called Orbital has filed plans with the Federal Communications Commission to eventually deploy up to 100,000 data center satellites, aiming to deliver 10 gigawatts of computing power, specifically to meet the exploding demand created by artificial intelligence. Jeff Bezos' Blue Origin has entered the same race, filing its own plans for something called Project Sunrise, a proposed network of over 50,000 satellites operating in sun-synchronous orbits. A company called StarCloud has already launched a satellite carrying an NVIDIA H100 GPU into orbit, making it the first company to run a large language model on powerful AI hardware beyond Earth, using Google's open-source Gemma model as its first orbital AI workload. Now here's where the story gets genuinely interesting, and where quantum computing enters the picture. All of these orbital data center projects announced so far are built around classical computing hardware, GPUs and CPUs, the same fundamental technology sitting inside every laptop and server on the ground. But a separate, smaller wave of companies is specifically asking whether quantum processors, not just classical chips, could eventually make the jump to orbit as well. And surprisingly, when you look closely at the physics involved, space might actually be a more natural home for certain kinds of quantum hardware than a data center here on Earth ever could be. Consider what quantum computers actually need to operate. Many leading quantum architectures require extremely stable, extremely cold environments, shielded as much as possible from vibration, thermal fluctuation, and electromagnetic interference. Building that kind of environment on Earth requires massive dilution refrigerators, vibration-isolated foundations, and dedicated facilities engineered specifically to fight against Earth's own noisy, warm, gravity-bound environment. Space, by contrast, is already naturally cold, already largely free of vibration once a satellite reaches stable orbit, and increasingly being explored as a genuinely useful environment for delicate quantum hardware, rather than a hostile one. An Italian deep tech company called Rutonium is one of the clearest examples of this exact bet. The company is specifically developing scalable room temperature quantum computers, with the explicit long-term goal of eventually deploying them in space. Rather than fighting against the challenges of building quantum hardware that survives Earth's noisy environment, Rutonium's strategy leans directly into using the naturally quiet, naturally cold conditions of orbit as a genuine engineering advantage rather than an obstacle to overcome. Meanwhile, a very different but equally telling experiment is happening through a partnership between InnoSpace and Norma, 2 companies collaborating on what they're calling in-orbit quantum computing demonstrations. Their approach is refreshingly direct and practical. Rather than theorizing about how quantum processors might someday behave in space, they're planning to operate quantum processing hardware directly from an active rocket platform during actual flight, deliberately testing how sensitive quantum hardware responds to the extreme radiation, dramatic thermal swings, and intense structural vibration of a genuine real-world space environment. The data gathered from that flight is intended to become the baseline architecture for something they're calling the Space Quantum Computing Center, envisioned as a cloud-linked hub using quantum algorithms to optimize satellite fleet operations, accelerate deep space data analytics, and provide quantum computing resources to both commercial and government clients. Before going further into the orbital side of this story, it's worth understanding the broader context happening back here on Earth, because space-based quantum computing doesn't exist in isolation. It's actually part of a much larger shift, already reshaping how the entire data center industry thinks about quantum hardware in general. Inside leading supercomputing centers around the world, teams have been pivoting away from the long-chased goal of achieving standalone quantum supremacy and toward something more practical, tightly integrating quantum processors directly alongside existing classical GPU and CPU systems. IBM outlined this exact approach earlier in 2026, describing what it calls quantum-centric supercomputing, a staged strategy that begins with offloading specific, well-suited calculations to quantum systems, while classical infrastructure continues handling everything else. This hybrid approach is quickly becoming the dominant philosophy across the industry, not just in space, but on the ground as well. Companies like Microsoft, Rigetti, HPE, and Dell have all announced partnerships and platforms specifically designed to integrate multiple different quantum hardware providers directly alongside their existing classical supercomputing infrastructure. Analysts at Hyperion Research estimate the broader quantum computing market grew to roughly $1.4 billion in 2025 and expect it to nearly triple, reaching close to $3 billion by 2028, driven largely by exactly this kind of hybrid integration work rather than standalone quantum breakthroughs alone. Government policy has been pouring fuel on this fire too. In May 2026, the United States Department of Commerce announced an investment of more than $2 billion specifically aimed at accelerating the commercialization of quantum technology. That kind of sustained, large-scale government backing signals that quantum computing has firmly moved beyond being treated as a purely academic curiosity and is now viewed as serious, strategic national infrastructure, the same category of technology investment historically reserved for things like semiconductors and advanced telecommunications. This ground-based momentum matters enormously for the orbital quantum computing story too, because it means the underlying quantum hardware, control systems, and software stacks being refined right now in Earth-based data centers will almost certainly form the foundation that eventually gets adapted for orbital deployment. Nobody is starting the space quantum computing effort from scratch. They're building directly on top of rapidly maturing hybrid quantum classical systems already being tested and refined inside terrestrial data centers today. That said, moving any of this hardware into orbit introduces an entirely new category of engineering challenges that simply don't exist inside a climate-controlled data center here on Earth. Radiation is probably the single biggest concern. Space is constantly bombarded by high-energy particles and cosmic radiation that Earth's atmosphere normally shields us from entirely. This radiation can cause what engineers call bit flips in classical computing systems, sudden random errors caused by a stray particle striking sensitive electronics. For quantum systems, which are already notoriously sensitive to even the tiniest environmental disturbance, the radiation environment of space represents a genuinely serious open engineering question, one that experiments like the InnoSpace and NORMA in-flight quantum demonstration are specifically designed to help answer with real data, rather than theoretical prediction alone. Thermal management in space also isn't quite as simple as the phrase "space is cold" might suggest. While the vacuum of space certainly lacks the ambient heat problems Earth-based data centers struggle with, satellites in direct sunlight can actually experience extreme, rapidly fluctuating temperature swings, alternating between intense solar heating and the deep cold of shadow as they orbit the planet. Engineering hardware, especially delicate quantum hardware, to reliably withstand those dramatic, repeated thermal cycles requires careful, specialized design work that differs significantly from simply relying on space's overall coldness as a passive cooling advantage. Then there's the practical challenge of maintenance and upgrades, an issue that barely registers as a concern inside a terrestrial data center, where technicians can simply walk in and swap out failing components, but becomes an enormous logistical and financial challenge once your hardware is orbiting hundreds of kilometers above the Earth's surface. Unlike the International Space Station, which benefits from periodic human visits and servicing missions, most proposed orbital data center satellites are designed to operate autonomously for years at a time, without any realistic possibility of physical repair or component replacement if something breaks. That constraint places an enormous premium on radiation-hardened, extremely reliable hardware design from the very beginning, a bar that's already difficult to clear for classical computing systems and considerably more difficult for delicate, still maturing quantum hardware. Given all of these genuine engineering hurdles, it's worth asking honestly why so many serious companies and research institutions are willing to invest real time and real money chasing this idea right now, rather than waiting until quantum hardware fully matures on the ground first. Part of the answer comes back to the specific advantages orbit offers that simply cannot be replicated anywhere on Earth: truly unlimited, constant solar power, genuinely free passive cooling once thermal engineering challenges are solved, and increasingly critical strategic and defense motivations around secure, resilient, quantum-protected communication and data processing that doesn't depend entirely on vulnerable ground-based infrastructure. This is where the second half of our title comes into play, the idea that classical computing simply can't keep up. That claim deserves careful unpacking, because it's true in some very specific, important ways, and considerably overstated in others. Let's start with where it's genuinely true. As AI workloads and satellite data volumes continue to explode, purely classical computing infrastructure faces a hard physical ceiling driven by energy availability and cooling capacity, both on Earth and, to a lesser extent, in orbit as well. Even space-based classical data centers, despite their access to abundant solar power and free passive cooling, still face fundamental limits on how much raw computational throughput you can squeeze out of transistor-based chips before running into diminishing returns. Quantum computers, at least in theory, offer a genuinely different kind of scaling advantage for a specific, narrow category of problems. Certain optimization tasks, certain simulation problems, and certain forms of pattern recognition across enormous, high-dimensional datasets, exactly the kind of workload satellite constellations generate constantly. If quantum processors can eventually be reliably operated in orbit, they could theoretically tackle categories of problems that would require impractically large amounts of classical computing power and energy to solve using traditional chips alone, even with unlimited solar power backing them up. But here's the crucial caveat that responsible reporting on this topic has to include, and it's a big one. The European Space Agency, one of the most credible, deeply experienced institutions actually working on real satellite data processing, installed an actual quantum computer inside one of its own data centers in July 2026, specifically to study how quantum hardware might eventually help process Earth observation data. And the agency was refreshingly blunt about the timeline involved. According to ES's own research, conducted 3 years earlier through a study called QC4EO, genuine quantum advantage for full-scale satellite data processing remains at minimum 15 years away. What arrived at their research facility wasn't a production upgrade ready to replace classical systems. It was a precision research instrument specifically meant to help scientists understand exactly what quantum hardware can and cannot yet do with real satellite data, while acknowledging plainly that the technology is still far too early stage to answer that question definitively today. That single, carefully sourced timeline estimate matters enormously because it directly tempers some of the more breathless framing you'll find elsewhere online about quantum data centers imminently replacing classical infrastructure in space. The honest, current state of affairs looks less like an urgent changing of the guard, and more like several parallel early-stage experiments, all trying to figure out whether quantum hardware can even survive and function reliably in orbit at all, well before anyone can meaningfully claim it outperforms classical systems on real, practical workloads. Still, even with that healthy dose of caution, the direction of travel here is genuinely significant and worth paying close attention to. Just a few years ago, the idea of any data center, quantum or classical, operating meaningfully in orbit sounded like distant science fiction. Today, real hardware is already up there, real companies are filing real regulatory paperwork for tens of thousands of satellites, and multiple credible research institutions, not just speculative startups, are actively running real experiments specifically testing how quantum processors behave under actual space conditions. The gap between fantasy and functioning prototype has closed dramatically faster than most casual observers realize. Defense and national security applications are quietly playing an enormous role in accelerating orbital computing more broadly. Axiom Space's own orbital data center nodes were explicitly designed to accelerate deployment, specifically to meet demand from defense applications requiring real-time, cybersecure, and quantum-secure data processing. That phrase, quantum secure, points toward another entire dimension of this story that often gets overshadowed by flashier headlines about raw computational power, the growing importance of quantum-based encryption and quantum key distribution for protecting sensitive satellite communications from increasingly sophisticated cyber threats, including the looming, well-documented risk that future quantum computers could eventually break today's standard encryption methods entirely. China, notably, has been a genuine pioneer in exactly this specific corner of the space-quantum intersection for years now, having launched the world's first dedicated quantum communication satellite, known as MISSIS, all the way back in 2016, specifically to test ultra-secure quantum-based encryption over vast orbital distances. That head start in quantum communication technology, distinct from quantum computation but closely related in terms of underlying hardware challenges, gives China a meaningfully different competitive position in this broader space quantum race compared to countries and companies just now beginning to seriously explore orbital quantum computing hardware for the first time. So where does this leave us? Practically speaking, if you're trying to separate genuine near-term reality from longer-term speculation happening across this fast-moving space, the quantum side of that same race is considerably earlier stage, currently defined by targeted research experiments, promising but unproven engineering bets from smaller specialized companies, and refreshingly honest institutional timelines, like ES's own 15-year estimate, reminding everyone that genuine quantum advantage in space remains a longer-term goal rather than an imminent reality. What makes this story worth paying close attention to isn't a dramatic claim that quantum computers are about to replace classical infrastructure in orbit overnight. If that turns out to be true, even partially, the eventual combination of space-based infrastructure and quantum computing could end up solving two of the biggest bottlenecks facing modern computing simultaneously: the enormous energy and cooling demands driving up costs on Earth, and the extremely delicate environmental requirements that have kept quantum computers confined to specialized labs for the entire history of the field so far. We're still in the very early exploratory chapters of this particular story, filled with promising experiments, ambitious regulatory filings, and honest, carefully qualified expert timelines rather than finished, working systems ready for widespread commercial use. But every one of the individual pieces required to eventually make quantum data centers in space a genuine reality, working orbital infrastructure, serious institutional research interest, dedicated startups placing real engineering bets, and a clear, well-understood strategic motivation driving continued investment are already actively in motion today, not sitting somewhere in a distant, hypothetical future. It's also worth thinking about how this story might unfold over the next several years, based purely on the pattern already visible in the broader orbital computing race. Classical space-based data centers are almost certainly going to reach meaningful commercial scale well before their quantum counterparts do, simply because classical hardware doesn't carry the same extreme sensitivity to radiation, vibration, and temperature swings that quantum systems do. Expect a steady stream of small-scale demonstration missions over the next several years, similar to the InnoSpace and Norma in-flight test, each one gathering real-world data about exactly how quantum hardware behaves under genuine space conditions, rather than any single dramatic announcement claiming quantum computers have suddenly, fully arrived in orbit. ES's own carefully sourced 15-year timeline for genuine quantum advantage in satellite data processing is a useful anchor point here, a reminder that serious institutional researchers are planning for a patient, methodical multi-year journey, not an imminent, sudden transformation. That patient timeline shouldn't be mistaken for a lack of genuine progress, though. 15 years might sound distant when you first hear it, but remember that just 5 years ago, the entire idea of any data center, classical or quantum, operating meaningfully in orbit sounded like distant science fiction to most people outside the aerospace industry. The pace of progress across this entire space computing sector has consistently outrun conservative early predictions, and there's a reasonable chance the same pattern repeats itself here, with orbital quantum computing arriving in some meaningfully useful, if narrow, form considerably sooner than today's most cautious estimates currently suggest. Whether that future arrives primarily through classical GPUs processing satellite imagery in orbit, or eventually through genuine quantum processors solving problems no classical system could ever practically handle, the direction of travel points toward computing infrastructure gradually expanding beyond our planet's boundaries, driven by energy economics, strategic necessity, and the sheer physical advantages space itself has to offer. Make sure you're subscribed, because this exact intersection of space infrastructure and quantum computing is moving faster than most headlines suggest, and we'll be right here breaking down the next major development the moment it happens.